And oh, by the way, like I put the chat list on Discord as well. But I have removed the any private messages, so I think it should be fine. So just maybe some of you guys are interested to look at uh, what someone else has written. I don't know. I guess there should be no privacy there. Like in the sense since when you're in this one now, then you can see what everyone else is typing in the chat box anyway. So okay, and I guess last time we ended somewhere like this, where we gave a very high level introduction on machine learning. And let me just repeat a little bit what we talked about last time. So say like you have like an application just want to recognize a cat from images. So I have like uh, this. Oops, I hate this thing. I need to move this aside so I can. Yeah, okay. So I have this, let's say, a set of cat images and then set of like non-cat images. So I have a data set here. So basic machine learning is just something very simple, like intuitive. We have a model that can be parameterized or like characterized by some parameters, like theta here. And so with different features, I can build a different function here. And based on this function, I'm going to, uh, let's say in this case, going to estimate whether an input is a cat or not a cat. If it's a cat, then I will have an output score is 1. Otherwise, I will get output score 0. So then I can create a loss function that is a function of my parameters. And basically, this will be just like sum over all the errors that may happen basically if I'm pulling images from the cat data set. I'm hoping like my f theta should be equal to 1, right? So then I can just like add all together like, whenever it's not equal to 1. So it's like I just sum over f theta I minus 1 for all the I in the data set, in the cat data set. Or like I should say the data set with the cat images. Yeah, but for simplicity, I just split like this. So typically what happens is that you have one data set, D, and then you have like images have the corresponding label, right? So actually, um, yeah, I write it in a, yeah, okay, it's okay. Maybe this is simpler, at least look at it this way. Or maybe I just a side note, like what typically you will see is that people will have like L theta maybe is equal to sum over all images in the data set. And then I have F theta I minus that what is the expected like label. Maybe I call the label is G I, something like that. So G is given, like um so this is like you know what it's supposed to be, like given the data set. And then like yeah, the loss function, as you can see, like if I have theta is able to I mean for the parameter theta, if my model is can ideally classify all the images, then the loss will be equal to 0. And then like yeah, that's so therefore the goal is basically I want to tune the parameter theta here, right? So I just want to tune theta such that the loss is minimized. So of course you need to be careful. Like we are playing with the training set only, right? This is a training set that is given to the problem and to your model. And in practice, if your training set and the testing set have different statistics. So for example, like maybe you have the training set is generated like when you're taking photos like outdoor under bright sunlight. Um, and then like when you test it, like when you're doing it indoor, like when it's the light is very dim, then maybe you don't get a good result because the training set and then the testing set have a very different like um, kind of statistics. So so this is one thing you should be careful with. And oh, wait a sec. My screen sharing is paused. Like, why is so? Oops. Okay. Oh, okay. I'm sorry about that. Like, it's yeah, yeah, yes. I'm sorry about that. I guess I when this kind of Zoom UI is like kind of blocking me somehow. I try to move it away, and uh by accident I press pause share. So um okay, I guess you can see my screen again. So maybe I repeat a little bit again. Like so, we have the loss. We generate the loss. Maybe this is the I just say like typically we see something like that, right? So it's like you pull out for all the data or data points from the data set there, and you just want to match or fit your model such that it's equal to your expected output. So I have my expected output is GI. So in this case, it would be like if the image I is a cat, then I will have GI equal to one. If like I is not a cat, then it would be like GI equal to zero. So then I will have my loss function will be simply the difference of my f theta I, that would be like the output of my model minus GI, and I just sum over everything. So if I can't like uh train the model ideally, so then the loss uh function in this case, like the loss here will be equal to zero. So that's our objective basically in terms of training the model. Um, any questions here? And one thing, note that like this is like also so-called the supervised learning, right? Supervised because in the sense that let me try to improve my handwriting. Supervised learning. So supervised in the sense like you know exactly what you're going to see like for your each of the data points in the data set. So you know the label basically. I know that like for each of the image in the data set, whether it's a cat, whether it's not a cat. So and there are two in the extreme case, extreme opposite case of supervised learning will be unsupervised learning. So in that case, you have the data set, but your data set is not um, I mean, each of the data points there, you don't have the label. For example, you just have like a stack of photos as your data set, but it doesn't say anything whether this contain a cat or this is a dog or something. You don't have any labels for the data set. And you still want to get some information, I mean, extract some knowledge from that data set. That's the goal of like unsupervised learning. So I mean, uh, this terminology keeps changing. Honestly, I guess at least like most people interpret like as what I said, like unsupervised learning as. I mean, for what I said, it's like not controversial, but maybe like a decade ago, that people think of unsupervised learning would be thinking about clustering, something like. But now things may change. For example, like a recently there's something like very hot, like in machine learning areas, so-called self-supervised learning. So so you can think of self-supervised learning as a form of unsupervised learning, but it's not clustering. Basically, what we try to do here is that self-supervised learning. Maybe I is that like you uh I don't have again I start with data that's not labeled. So I have the entire data set is not labeled, but I still want to take advantage of that. So it's like same idea of unsupervised learning, right? Take advantage of the non-labeled data. But in kind of like a decade or 2 decades ago, when people think of unsupervised learning, they will imagine, okay, the only thing I can do will be try to cluster the data. For example, like I have these images, have cat and non-cat images. Maybe based on like the similarity of these images, I will just group images that looks like a cat, then I'll group them together. Then that's the clustering procedure. And then like things is not like a cat or like you don't know which one is not like a cat or not like a cat, right? What I want to say is like we'll just group like images that are similar together to different groups. That's what clustering do. But for self-supervised learning, what we will do there is like maybe I just give an example. For example, like a really classic example for self-supervised learning will be for do NLP, to natural language processing. For example, if I have think of the classic problem of translation. So maybe I need to translate some text like from English to I don't know for any other languages, or maybe to Chinese or Japanese, right? So I can do translation of like maybe you can use Google Translate or something, but that's exactly what they did there, right? So I have some sentence like in English and then you're trying to translate to Japanese. So I can make it a supervised learning problem. For example, if I can build a data set that contain each of the sentence, maybe I speak English, then then maybe Japanese is a watashi wa 英語 ego or ego ga, I guess. I don't know. Ego ga maybe harasemas or something like that. So I don't want to write it anyway. So in that case, like if I have a bunch of sentences, right? So then for each of the sentence, but even that will be difficult because if I just have the sentence, but like if I want to translate that, I want to precisely like speak actually can speak actually I speak I can speak should kind of like correspond to like maybe harasemas here. So, but um, so even if you just have a list of like examples, it's actually not trivial like to immediately build a translation model. Um, and not to mention that like in this case, I need to have like corresponding sentences like one at a time, right? So that is not what people do now because you cannot find easily like corresponding sentences right from one language to another language, right? But instead, like what we can do is like if I use like maybe self-supervised learning, it's like I don't care about like whether I have corresponding sentence from one sentence to another sentence, but instead first try to build a model for each of the language, right? I build a English language model and I build a Japanese language model. And then afterward, like I have the model, then I fine tune this model. Basically, I have a model now. Then I am going to have the model maybe like for each of the sentence coming up, like input to this on one side as English. Then I will first like from this model, I will have some features, and then like these features will be plugged into my Japanese model to output the sentence there, output a translated sentence there. Then the key here is like how do we build the model? And in terms of building the model, it's very easy, like with self-supervised learning, because you think of like, or like I shouldn't say easy, but in the sense like you don't need to pre-process any data set. So it's not like you don't need to generate a data set of like one sentence in English correspond to another sentence in Japanese. I can just look at all the tests, maybe tests in Wikipedia or like any test online. I can generate a model following way. I can just train a model as a predictive model of the language. In other words, like if I have like each word at a time, let's say I can speak here. Now my model will be just building a, let me really need to improve my handwriting. I can speak here. So can be just a predictive model, giving what I have in the past as my input into the model. I'm going to try to predict my next word here. So, and uh, and of course, in this case, it will be a supervised learning, right? Because I can just in, input like any document like from Wikipedia, I can just like take I mean consecutively uh some words coming in, like let's say I have a long paragraphs and maybe like inside paragraph I can speak something here, then I can just cut out like what I have earlier as the input, and I will input the next character as not sorry next character next word as my output, and then like this will be a label that is given, right? So then I can use supervised learning. So is that clear? And we will say like the process to train a model like this, like often like in the self-supervised learning as like p-test task, and then afterward like we refine whatever this model like for further, I mean application that you are interested in will be like, for example in this case if it's a translation, it will be the downstream task. So um actually, maybe I will talk more about like self-supervised learning like in the future, but uh, just give an overview here. So let me go to the slides instead. I guess I maybe it'll be better than my uh, that uh, don't need to bear with my handwritings at least for the moment. So here is a some slide I kind of like stolen from this website Deep Learn. Again, I mean, like this is a very high level. Like, don't take everything as granted. Like this is a supervised learning or managed supervised. I think this term is it's not very popular to me. Like, um, semi-supervised learning is just similar to supervised learning, but like you have some labeled data and some unlabeled data. So you have the data set. Some of the data is labeled, some of them are unlabeled. It is you can think of like, for example, the self-supervised learning we just mentioned is like a kind of a special case of semi-supervised learning. Um, and also there's reinforcement learning. We may talk about that like, yeah, we should talk about that like, but in the future. It is a but at high level, like the difference right from reinforcement learning and the self-supervised, I mean with like supervised learning, unsupervised learning is that like this is used for application like there's some degree of like supervision, but the data didn't teach precisely what the model is supposed to do. For example, like I can have application of like self-driving car. So I have input like it's like the what the camera is seeing at each moment, right? It's like camera is looking to the front, and then like based on like the whole environment, then it I may have supervised data like try to say in the sense whether the car is doing good or bad. Doing bad will be like, for example, like it cannot stay in lane, then it's bad. So then that would be some feedback. Okay, your car is like staying off lane. But know that like this is not really supervised in the sense that like I the 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 feedback here, I mean the data set here didn't tell you like if you something like that, like you see whatever there's a car in front of you, or like whenever like I don't know, there's a stop sign or something like how how much you should turn the wheel, right? Because precisely if you need to control a self-driving car, the agent need to know precisely the action, right? The precise action will be like how much you should turn the wheel, how much you should press the gas pedal, or like when you should press the brake and so on. This information is not given in the data set. What is given is just some hints, basically saying like whether you are doing good or doing bad and so on. And you can see like for many real world application, you don't really have like supervised learning, but you will have like reinforcement learning. So anything related to control, like actually like nowadays like many people like just use reinforcement learning for everything, like for control applications that used to be use some classic control like like PID controller, so on, and you can build like reinforcement learner instead of like using this classic controller. Uh, and yeah, and that's basically and this is another slides I'm stolen from online. I guess yeah, maybe I was just skip it because as I mentioned, this terminology keep changing over times. Uh, Especially clustering. Like people think of unsupervised learning, usually think of clustering in the past, but it may not be true anymore. Um, I'm not sure even. Yeah, probably I should remove these slides in the future. So and yeah, okay. Anyway, yeah, but this like in terms of supervised learning though, like I guess classification and regression here is like quite uh um what's that word, like universally agree with most people. So when you have a supervised learning problem and you kind of like classify into a discrete number of classes, like in our cat example that is like classified into classified into uh cat and non-cat here, then this is a classification problem. So basically your output here is just a, in this case actually binary classification because it's just 1 or 0. So and if you have like multiple classes, maybe I have a dog and a human and a cat, and then it's still a classification problem with like a finite number of classes. But on the other hand, if you have like something uh infinite number of classes, for example, like if you trying to predict the house price given some information here, so it's like predicting price. Then in that case would be a regression problem because yeah, you unless you want to put into categories like finite categories like um, certain amount dollars like below 10,000 and then 10,000 to 20,000 and so on and so forth. Uh, yeah, I don't. You cannot buy a property for 10,000. I think. So this is some example like using neural network. Actually, this is pretty old, like 2012, I guess. Back to this is like for the Imagenet competition. Just classify an image with is showing the highest the the highest score like class determined by the model. So for example, this the ground truth is a query here, and it's like making a correct classification, not the most correct one, but it's in the top 5 classes. And this one you think of is just not classified very well. It's the ground truth because a scat bad. I don't know what's that exactly, but it's a classified with this earthworm and so on and so forth. So we'll talk about, of course, in more detail, like how do they do that. But here's just some example, more examples. Let me just skip that. So a little bit history. You can see like the modern neural networks. I, I'm not sure I should put it that way. Or like um, neural networks get back into the spotlight. It's the in the year of like 2012 when the model is actually by Jeffrey Hinton. Uh, com, com, Basically like just win the competition in ImageNet, and ImageNet, by the way, is a competition hold by held. Yeah, I should. So, yeah, so it's held. Yeah, that was held by Stanford, like Stanford University every year. So and that's like one category of the competition is like image classification, like this one I just show here. So you have many images, you have 1,000 classes, I believe, and then you have like millions of images as a training set, and then you just want to classify each of the image, like what was supposed to be the category. And I mean, before 2012, like the best approaches are this classic approach. So classic approach in the sense like you have the image, you just try to generate some handcraft features for example, this HOG, LBP, and so on. Then afterward, like you may do some post processing of your feature. Then you do classification basically. So classification using like machine learning model, for example, supervised machine. That's what people win the competition like before 2012. And then afterward, like people just have this neural networks models training end to end. People like to call it end to end because in the sense that no longer you have a kind of handcraft feature generation. You basically engineer is like more or less like move out of the picture. Like it used to be like people like have earned their life by like designing features, like kind of like determining what kind of feature is good, like from the image or like from the input. So nowadays it's getting more and more like you skip the step. Like instead of, I mean, as long as you have like enough data, you can simply just like put in the data and then train the entire models. And hopefully, like the early layers of the model is going to generate you the features, the appropriate features. And there's more lectures. We'll talk more about that. Yeah, we'll talk about there's some classification error. So you see that people got so excited because I before 2012, people thought, okay, yeah, we cannot get much better. Like you see the gain like from the last year is quite tiny, but then like we have a huge gain using neural network training end to end. And then afterward, like the gain is yeah, have continuous gain like, as the lateral models improve. So I guess I won't go too far into this. I will go back to this later on. So and yeah, yeah, I will go back to this later on. But one thing to mention again like, is it's quite amazing that so at least like we can claim uh in theory. No, I'm not so say in theory. Uh, roughly speaking, I'm not even this is a good phrase for that. So we are doing in terms of classification, we are doing better than human. I guess last time I mentioned that also, like, but this is just one data point. So yeah, these things I mean it's also known as representation learning. Essentially, like when we have this feature learning here, so it used to be like the feature is generated by human, but instead like this feature is like learned by machine now, learned by the model, learned by the neural network. And that's like a whole discipline of representation learning, or even a new conference, the conference of like represent ICRL, I think it's a International Conference of Representation Learning. Um, and that's basically kind of organized by, founded by the neural networks people there, like by user Banjo in I think he's involved. I'm not sure Hinton was involved, but I'm quite sure like Banjo is involved in organizing that conference. Um, and so this is just another kind of illustration for that. Like it used to be, we have this step like is image feature generation is like by some human by some engineer, and then after like generating the feature, then we uh, we're going to use this feature to train a classifier. Um, but now it's like everything just one step here. So okay, I guess I mean yeah, we will all go back to this in more detail like when we talk about CNN. So don't worry about that. Uh, but here's just like a couple more examples like how maybe to motivate you guys like this why it's so interesting. Nowadays people get so interested and excited. So you see like they're doing really great like for localization. I mean you can play with that's called YOLO. Um or like that's YOLO is just one particular work by I think it's like University of Washington, but there's other like approaches, but YOLO is very kind of like famous to do object detection, and they have like keep improving different version like YOLO 3, YOLO 4. I guess the latest is YOLO 4, and you can do something like this, like very pretty good. Like you also have this confidence here given here. You can see like it's doing great job in terms of confidence. Um, and yeah, let me yeah, this is just a okay. Let me skip this. I mean, this is just you can do even more kind of precise in terms of like determining the location of the target. So you can do a object segmentation, precisely get the where the person is, like where's the clock and so on. And you can also do like accurate pose estimation. And I'm also captioning, image captioning. So I mentioned last time, I guess if if you consider like this is some form of image understanding, then like at the moment, like the model is doing quite well. But again, this is basically all statistics. So you see, this is all quite cool. Eh? I mean, the label is quite accurate. You have like young girl in a pink shirt is like swinging on swing. Uh, let's see. I don't have any bad example put in here. Yeah. So, but also like again, like this kind of stuff like is progressing really quickly. Um, I didn't really because it's hard to catch up like for all of this because all of this kind of each of these whenever like people start doing like a work like this and then realize okay yeah you can use neurology to do that, then like other people try to like beat their results and so on and so on, like so for each of these problem like progress really quickly. So it's a dance image caption, so I guess it's not you can do this kind of visual question and answer as well. So based on the image and given a question and maybe try to answer some. This is much harder though, like apparently. Um, and yeah, let's skip that. Right, and of course you can use this for classic image processing application. For example, like nowadays you can get much better supervised solution using neural networks than like classic neural networks. Classic image processing techniques. Um, and also like you can generate art or like you can use as a tool to generate art. And this is a very interesting work that like you can change the style of whatever your input. Like for example, like based on different style here, like I have like style, like this is a sample style of the painting, right? So different style. I'm not an artist. I don't remember the name of this painting. But then based on the style and based on the input of the image, then you can change the style of the input. So and yeah, this is something similar. We'll talk about that like later on as well. Honestly, uh, yeah, I think I think we'll talk about it. So and the application I just mentioned is mostly for computer vision, but there are also many applications are not computer vision, right? So machine translation, there's lots of application in NLP, uh, and and as I mentioned last time, like the problem is like for people like me, like in academia, I think like we cannot do much about it because like machine translation is dominated by industry. For example, like they really like they can cost millions or tens of millions to train a model, so it's not affordable in academic setting. So for example, like OpenAI have this what do they call like the GPT-3 model just several months ago, like it cost several millions. But then later on, like Google has actually something competing. I forgot like the name of the model now. It's but I remember it's like 10 times bigger or something like that. So yeah, so I don't know, I don't remember how much they spend in training that models. But anyway, for those things, I probably not um yeah ideal like research problem like in academic setting. And of course, I reinforcement learning, like we mentioned reinforcement learning, right? So we can like combine neural networks into reinforcement learning, like have this so-called deep reinforcement learning, and can do very interesting thing. Like uh of course, like self-driving car is one thing, but many people like will first consider gaming, I mean computer games and so on, like as a sandbox to train this reinforcement learning model. So, for example, like DeepMind is like has been okay. Do I have oh, okay, link to YouTube actually. Oh, that's a advertisement. Oh, so yeah, let's forget it. Yeah, anyway, you can you can play that. So, uh, all the slides on the website, right? So if you're interested, you can click the link. So it's just like trying to teach um this player or like auto, I mean teach the computer to play the Atari games. Um, and of course now it's more than Atari games. Like there's Alpha Star I mentioned last time. There's playing StarCraft, and there's also what's the other game I forgot. They also tested that. Uh, I forgot. Yeah. Uh, yeah, I forgot. Yeah, it is okay. So I'm also AlphaGo, right? AlphaGo paying Go, and yeah, I will skip this also. Like we probably will maybe yeah, probably we have chance to come back to that like in more detail. So okay, let's start like to talk about like some maybe history and like maybe high level neural networks. So it's something like honestly, the whole thing is very simple. It's nothing really so. The great thing about neural networks, I guess, to work on this is like it's actually the tools in neural networks is very simple. It's like it's easy to understand and but it's at the same time very powerful. So of course, as the name suggests, like is related to the biological brain, and you can use that like for many different kind of problems that you can do supervised, but also you can do like unsupervised problem. Like, of course, in that case, I probably you need to formulate into a self-supervised learning problem and so on and so forth. Yeah. So for people interested in neural networks, of course, I uh, it may be like people yeah, in the biological field, and then maybe they want to study the brain but cannot study directly. Maybe they can look into like build model, like in model like will be neural networks, right? So one possible model. So, but of course, like for us, we are not. Well, no, I don't know. Like, yeah, some of you guys actually from biology background, but not precisely, I guess, not neuroscientists, I guess. Um, for us, like in this course, is mostly focused on how we can use like both ideas from a biological network and then can be used like to solve problems. Um, and yeah, let me just go a little bit statistics of our brain here. So it's just for fun. It's actually very it's not heavy, like it's just like 1.4 kilogram, like approximately. Uh it's 2% of the weight, but actually consume like 20% of the energy. Uh but still like 20% is actually not a lot. It's like 12 watt or something. So uh, when I think of that, we're really efficient things. I mean efficient uh yeah, biology is amazing. Like we are spending like less than 100 watt like living, and it's less than a light bulb, and we can do lots of stuff, right? And compared to a GPUs, I say you think of a GPU servers, you're using like 1,000 watts. So actually we're extremely efficient. And of course, the brain is just connected by neurons. It's just composed of neurons. They're interconnected with one another. So this is an example of a neuron. So we have that astron, like basically like uh I think like how does that work? So yeah, we have this dendrite here. It's like collect chemicals, and then like based on like what they collect here, then they will fire. So if fire, but actually fire is not in terms of like amplitude, it's usually in terms of pulse. So um, for example, when it's excited, like then it will fire rapidly, like multiple times, like with the same intensity, but you get excited fire like rapidly. And then when you fire, it was kind of like it will transmit the signal through this axon, and this axon at the ending it will again generate chemicals, then it will propagate to another neurons and so on. So the simple model, what we use is like that's basically like what people usually think of artificial neuron. Is extremely simple, right? So we have inputs here, then we'll just weight sum the input, like with set of weights. And this weight will be tunable. That's basically the part we are going to tune inside the model. Um, and then with the sum here, it will go through some activation function. So this activation function is emulating uh, whether you're firing, right? So like, for example, if you have collect enough chemicals that the neuron get excited, you fire it. Otherwise, you won't fire it.
Dr. Cheng,
Yeah.
are the weights there? Are those the same as the parameters that you were talking about earlier?
Oh
Or
yes,
are they
they're essentially the parameters that you
okay?
can tune. Yeah.
Thank you. Just thanks.
Uh, and and this is one neuron, right? And if you have multiple neurons, you can just cascade them, right? Or like put them into a layer and then cascade the layers one at a time. So and then and you can also like put it into a matrix form, right? So yeah, probably I will get more into that like later on. Don't worry about that. So yeah, for the math, I'll get more detail next time. Uh then but here I just want to emphasize like okay, what's the difference of deep learning from like classic neural networks? Like for a long period of time, like people don't know how to train a network model with like more than two, 3 layers. So when you have like more than 3, 4 layers, like basically it's not trainable. Um, somehow you just they try, but it just doesn't work. So then since like a decade or two ago, like probably around like 2005, like people start to know lots of different tricks to allow them to train like a deeper and deeper model. And it turns out that once you use these tricks to be able to train a deep models, this deep model just beats all the previous kind of machine learning results. Like basically, for a long period of time, people uh, are very much like kind of think that okay, we are basically like peak, like we cannot get even further. But then once they have this deep learning model, suddenly like they just beat whatever they have like in the past easily. Um, so a very brief history of artificial neural network, and okay, I'm not really good historian. I'll just like flip through that like very quickly. I guess some highlight here is just you see like this is really old. This is not something new. It's dated back like in the 40s of last century. So it's like very old stuff. And you may heard of some of this name like Herbian like theory also like appear in like um, neuroscience. That's basically like uh, they thinking like okay, if you use the I mean basically the little one is plastic, it can change, and then like, the more you use it, that then it will just more stimulation, then you increase that the contribution of that neuron and so on and so forth. Um, and for a period of time, like until 70s though, like all these methods are a bit ad hoc in the sense like if you need to train the model, how I'm going to train it. So remember, like we have the W or the thetas are the parameters, right? So what they did until 70s are basically just okay. I adjust it like water at hotly, I change it in one direction and then change it another direction, and see if I decrease the loss. If I decrease the loss, then it's good. If not, then I change it another way. So it's not a very efficient way of training. So then, but even that, like when they first initiate that, like in the 40s and 50s, initially there's a lot of hype, like in 50 or something. Like people even think, that's actually quite crazy. They think I have like 100 new ones now. I can identify. I mean, I can recognize this is a tank. It's not a tank. Like again, like military is driving all the research. Okay, they that's lots of hype, and that's at that time. But then immediately it doesn't work, right? People realize it doesn't work, and we went into a dark age, and our current like computing models I just dominate. And our current computing model is like with this memory, hard drive, and so on. Like this Turing model, like it's actually by Turing and also like by von Neumann as well. Something interesting. Ironically, von Neumann himself is really interested in the neural model himself. Like he suggested to use neuron to kind of like to this kind of neural function like to build like telegraph relays and so on. But of course, it died early. I guess from Norman is a genius, but I've got like he died because he's in the Manhattan Project. I guess that he died of cancer as well, like in 50s. I mean, when he's not even past 60. Um, and But as I mentioned, like so when the hype died down, like one thing like why it died down so significantly because that's two very famous researchers, Marvin Minsky and like Simon Pepper. They wrote a book on perceptron. Is basically just multi-layer neural network. Basically, they have a fancy name called perceptron. Um, but the activation function like, is like I think they consider the step function as the activation function. Nowadays people call multi-layer perceptron. It's actually just mean multi-layer neural network, essentially. Most people, at least when they say it, they just mean that. Um, but about like the book by Marvin Minsky and like Simon Pepper, like the book basically have a proof just saying like what's the limitation of perception, and then like saying, but okay, the thing is like at that time like people didn't read the fine print as that as well. Like they mentioned the limitation, but they that limitation does not exist if you have many multiple layers. I'm assuming if you can train many multiple layers, then like the problem is will not be there. But many people like just consider because like in practice also they do not manage they did not manage to really make it work for real application. And also because of the famous book, then like we have the first dark age of like neural networks. I guess around like 60 or something. Um, and then like afterward, like people invented the backpropagation algorithm. Like it's back in 70s, but it's not popularized until 50s. Like it's reinvented like many times like by many people. Also like by Yana Kun, like he, as I mentioned, he's considered one of the big three of deep learning, and 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 that with that like it just get popularized. Like get suddenly like, people get excited by the area again. Like people start like going back to work on neural networks for a moment, for a while, and that's some I mean bloom for a moment, like until like uh late 90s, I guess, like mid 19 late 90s. Again, I will have another dark age because I uh Vladimir Vablik, like he proposed SVM support vector machine, and it's you can think of like in the sense it's a simplified model of neural network. Really, it's a yeah. We'll go into that also. Like yeah, next time maybe like later on. So and because mathematically it's more elegant and have nice theoretical model there, and also like in practice like you can get high performance as well with that amount of data. You because I honestly, because at that time the training data is we have less training data, and also like you have less computational power. It just looked like SVM is a much better solution. So everyone just jump to study like to do research on SVM instead. So therefore, like uh, unilateral like lost favor, and then suddenly, as I mentioned, like around 2005, like I mean, even though like I guess in the US more or less like neurolateral research has completely gone because the research kind of model here is basically you try to get funding from federal government. If you cannot get funding, you die. Basically, your research area die. So therefore, like in the US, I basically it's just wipe out. There's no one like study neurolaterals at all. And some people interested to work on neurolaterals just move to Canada. For example, Jeff Hinton himself, like he worked in, I forgot like whether he was in CMU or something. Like he moved to Canada instead because moved to Toronto. Yeah, because it's just no funding. So then but those people moved to Canada. Canada has a more favorable. I would say it's actually a better model. Like they fund everyone basically. Give someone everyone have a tiny small money just to let them survive. So then they so that the basically the research area does not like completely wipe out. So then people like they're still working on that. So and in 2005 or something like that, then they started to realize like, how to train a deeper model, as I mentioned earlier, and they're able to beat early results, and then so suddenly everyone got very excited and then moved back. I guess there's several. Besides, they introduce more tricks. Uh, One thing is of course GPUs. Because we have these wonderful gamers in the society just have this computing costs keep decreasing significantly because they are basically sponsoring the research community by playing game because suddenly like GPUs become like a consumer product that can be widely available like to researcher and yeah and also like data is very important as well like um suddenly like because probably with the internet and so on like storage is getting much cheaper like cloud storage is widely available. People are encouraged to whenever they generate data they put on the cloud as well, so therefore like there's many more label data and also like much faster and much more powerful computing resources available, so that also like let the basically the deep learning or neural ledgers to come back. So this is just some conclusion. I guess uh let's see what I have like well 20 minutes. Let's see what do I have here. Yeah. So I guess I want one thing I want to do here is I don't know how many of you already let me I need to pull the chat going up again. Let's see. How many of you have tried to install uh, Python and also maybe like some packages? So maybe here, I would just like, of course, I'm a bit biased. I like PyTorch a bit more. Maybe like I will just illustrate PyTorch a little bit. Of course, you can play with TensorFlow as well, but I guess the point is like if you don't actually even you have like I guess most of the time I guess if you have GPUs and you can it's good to try to install the things like on your own computer. So but yeah, often it's more convenient I guess. But you can also use Colab. So that's Colab Research google.com. So if you don't uh, let me use another account, maybe like just like to illustrate this. I mean, maybe I start a new notebook here. Just create a new notebook. So if you use Colab, you don't need to install anything. Basically, you can just go to the website and the stuff is on the cloud. You just need to have a Google account. And the nice thing is that you will have like some uh, available. Where is it? Let's see. Is that one time? Yeah, change one time type. You can take advantage take advantage of GPU as well. I don't know how much time you can use like for GPUs. But let's start with I've GPUs here. So now that I also have GPU for the for my Colab environment here, and so if I'm using Torch, then uh, by the way, like I already have a Python environment here. Like by default, is Python here. So I can, for example, if I can run something here, right? And by the way, if you don't know, of course I can whenever I press something here, of course I can run it. Where is one here?
Dr. Cheng,
Yes.
um, for Colab, uh, does it already have a Python environment, or do you need to set
It's
that
already
up?
Python environment, but you may need to install packages. For example, like it may not have to Torch, or like you may not have like TensorFlow there. I'm not sure like whether you have TensorFlow.
Okay, okay.
Yeah, maybe I can try. Yeah, I think you already have TensorFlow here. Yeah, you have import
Oh,
TensorFlow.
okay.
It's
Is
already have TensorFlow.
maybe there's a list of things that they
Yeah,
include by default somewhere?
yes, but maybe I try whether I have Torch. Oh, we could even add Torch here, so it's amazing. So
So if there was something that wasn't included, would you just do like a pip install or
yeah, you
something?
can pip install. So, but you want to have a exclamation mark first. So it's like escape out of the Python environment.
I
So I
see.
can try.
Yes.
Yeah, and pip install maybe. Uh, let's see. I don't know. Like maybe I try Torch
OpenCV or
Vision.
something.
Let's see
Sure.
if I have Torch Vision here.
Oh,
Yes.
it's already there. Wow.
Yeah. So and and oh, by the way, for you guys, if you're really new for Colab and also Jupyter environment, by the way, like that's you can look for the one here. I don't know how to where is the one here. If I press enter, it won't run the command. You need to press shift enter. So if I have something like again, I have 1+1 here. Oh, okay. For Python, like this pound sign here is just to comment whatever afterward, comment all the text afterwards. So um now I have torch here. Let's say I already import here. Let's here like I import torch here, and let's see I can see if the GPU is support. Like I've torch CUDA. Let's say torch CUDA current device maybe, or like current bus. I can look at. Oops, I don't know this. Oops, this combo thing is quite. So the current device is have a device 0. I can check or like I can even more explicit to see like if CUDA is available, like it's available, and also like the CUDA is initialized. Yeah. And I can also get the device name, like what is actually the GPUs is one name. Get device name capability. Oh, okay, interesting. I don't know that. Yeah, this is a Tesla T4. Um, so I will let you guys play with that. Honestly, maybe just like demonstrate the torch like create a tensor. So it's very similar to NumPy. If you play with NumPy before, like I can create a tensor of let's say like a matrix. Let's say maybe tensor 1, 2, 3, 4. So it give me okay. I need to close the bracket. Yeah, this gives me a tensor. So, and of course I can convert a NumPy array into a tensor. So maybe I have a NumPy array like x is equal to NumPy array. This is very annoying with this combo thing. I don't know how to turn it off. Anyone know how to turn this combo off? Like, I don't know.
I've never seen that before. Is that on the colab?
Yeah, it's on the collab.
Mm.
So maybe I have 1, 2, 3, 4 again. So maybe, yeah, I call this x something, right? Then I can convert this x into a tensor. It's just the same thing as before. So, but anyway, like, yeah, I would just let you guys to play with that. But I guess I just point out that if you don't have environment set up, or like, actually even like if you don't have a GPU, yeah, you can just take advantage with like collab. And yes. Let's see what else. So I have some time here. I'm thinking like whether I should get started with okay, so what I plan to do after next is a talk a little bit like maybe a little bit math review, and also like not exactly a lot of math review, but maybe talk about some classic machine learning model, just a couple of them, like basically linear regression and maybe logistic regression and SVM. So that yeah, I guess basically just that. So that um and 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 I'm actually like, if you think of SVM as I mentioned, you can really think of that as it's just neural network. So therefore, like what I introduce something is like linear regression is just, I guess, like to get use of like, or like give you guys some uh, chance to review some of this math, like for example like this uh, matrix math if you're getting rusty. So maybe I start a little bit and see like where we're supposed to end. So um so first of all, like let's say if I have uh so I have whatever matrix, like I can say like matrix A here. So I have a vector X here, something like that. By the way, like whenever like we talk about vector, like by convention, we'll assume this is a column vector. So let's say this matrix is m by m here, right? So I have like n row and m columns. That's what n rows and m columns. So therefore, like this is a column vector. So let's say this is just 1 by n here, like sorry, n by 1 here. Let's say n by 1. Um, and so let's see what do I need to, what do you guys need to know? So for example, like yeah, you should know transpose, right? So I make sure you know transpose, right? If I have a matrix, I do a transpose, it's just a flip it by like 90 degrees, kind of. So for example, if I have like actually, why I don't use collab to illustrate that. Um, So I have this tensor here. Let's say I call y is like this tensor here. Honestly, I'm more familiar with NumPy than Colab, but let's see. No, sorry, I mean NumPy more than like Torch, but For NumPy, I know this is the transpose, right? So I'm not sure torch is the same notation. Let's see, does it work? Oh yeah, it's the same thing. So and so the original matrix is 1, 2, 3, 4, right? So if I do a transfer, it'll be 1, 2, 3, 4, something like that. 1, 3, 2, 4. Um and yeah, put this side by side or something like that. And let's see, what do I want to? Okay, maybe I just make sure that if you guys are following me. For example, if I have x here is n by 1, so what is the dimension of x transpose here? Dimension of x transpose?
1 by n.
So is that Chris here? Wait, let me repeat again. So don't go so quick. Give a little bit thought about it. So x is a column vector. So therefore, like you can think about a column vector is just a matrix of dimension n by 1 here. So now I have this thing is equal to x multiplied by x transpose. My question is, of course, this is a basic matrix. Okay, so yeah, I'm not sure I should say it's a matrix. There's a chance it's scalar also. Scalar is a matrix. Yeah, so and yeah, what will be the dimension of this thing? Yeah. Yeah, I see like some of you guys are, yeah, get it right. Yes. Know that like if I have X transpose here, X transpose, the the dimension will be something like that. So the dimension, this is X transpose, will be 1 by n here. So I have like n by 1 by 1 by n here. So that will give me a matrix size of n by n. And you should remember like what is matrix multiplication. Let me erase some of this stuff. Maybe. So for matrix multiplication, so for example, like if I have like a matrix A here multiplied by matrix B here, so maybe this is a m by m, this is a m by k. Note that like I my the number of column of the first matrix has to be equal to number of row in the second matrix. Otherwise, you don't fit because uh, for A times B here, if I have a matrix A, B here, if I look at the ij element, it's just equal to, I'm going to take the ith row here. Let's say this is the ith row here, multiplied by the jth column here. So this is j column. Um, so multiply like, so a row vector multiplied by this column vector will be just equal to a scalar, because then this is actually equal to this first element multiplied by this first element at the second element of this row vector multiplied by the second element of this column vector and so on. So okay, just make sure how you know what I'm saying. Like, so what is 1, 2, 3 multiplied by 4, 5, 6 here? So maybe this is another question. So what's equal to that? What's this? Yeah, I think you're probably right. I don't. Yeah, I think you're right. Yeah, you're right. You're right. 14 plus 18. Yeah, I think it's 22. Yes. So okay. Yeah. So okay. So just a reminder of like matrix multiplication. Also like some matrix stuff. Um, and oh, by the way, then maybe I ask another. Yeah, this is a bit too big, but maybe I ask you like, what's 1 2 multiplied by 1 2 2 2? Let's say. Oh, you may need to. This is a third question here.
I'm sorry, Professor, I can't quite read that. What does it say?
Oh, yeah, this is 1 2 multiplied by 2 2 here. So this is a column vector 1 2 multiplied by row vector 2 2. So okay, okay. Okay, I assume that notation means that like above, right? Okay, as uh ditto, right? Okay, so yeah,
Yeah, sorry about that.
yeah,
Just saving some time there. I
yeah,
can type it out though if you want.
yeah. No, that's fine. Yeah. So yes. Yeah, I know this is very simple, but you know, like because if I don't ask it, like I don't know like whether you guys know or does not know. So like it can be like some silly questions, but um and yes, and actually, yeah, maybe since I have a couple, I think maybe like just end it like something like that. So how about like 1 2 3 4 1 1. So so this is like probably the last question of today. Yeah, actually, yes. Um, it's convenient. If you look at this here, um, it's a weighted sum of product of these two guys here. Like what I mean is, if I put this as x1, x2, y1, y2 here, you see like this is actually a very much carve shorthand for like if I carve a x1, I have like xi, yj, sum over I and sum over j. And this may be like a matrix W, I call this is a Wij element. Like, I mean, like for if I take from the first vector the ith element and then the second vector the jth element, and I'll weight it by like this guys here, the corresponding value here, and I sum them together is like basically that matrix. Of course, I don't know. This is just a remark. Yeah, I don't know. It's not. Yeah. Okay. I guess Okay. I guess I spend all the time. I guess maybe I'll just stop here. Then next time we'll just continue to talk about linear regression. I guess linear regression first. Then I guess as an example like of supervised learning. So if if you don't have any further question, I guess we'll just stop here and then I'll see you guys next week then. And by the way, please sign up to Discord and then drop a introduction, like just say hi, like what you suppose, or like what you were working on, or like what you like to work on, like what you think would be interesting, like can be work on like in the future. And I created an official like homework seal for that. So and it will be due like next Tuesday. So but it's very easy, right? So I assume that I just want to make sure that you guys will log into Discord. So okay, really, I will just stop here unless someone has other questions. Yeah, sure.
Professor, do you suggest any to read anything before the next class, just so that like I have an idea of like what to expect?
Oh, okay. I have you can go to, let's see, let me just let me share the screen again. Yeah. Share screen. So if you go to the course website and so yeah, I think it would be helpful if you take a look of this the classification regression, like something yeah, that should be helpful like for you guys. And if you you don't need to understand everything, like if you spend time reading that, like it should be helpful. So and it I don't know what to point you in terms of, if you I know someone like to read textbook or something like that. So I don't have like a particular textbook suggest for this kind of materials. Honestly, like you probably can just like Google like or like go for Wikipedia, for example, like you want to get an introduction of regression, like for example, like if for linear regression you want to know more and you're looking for something to read first, maybe like you can just first go for Wikipedia. Um, of course, you can go for any textbook. Like let's see, do I have put any mentioner? I think even the textbook by Banjo and so on, like they will have a chapter on that. So you can take a look of that as well.
Okay, Professor. Thank you.
Okay, so I guess I will just end this meeting. So unless someone else have other question.
Thank you.
Yeah, thanks. I will see you guys next week.
Yeah, see you next week, Professor.
Yes, yeah.